And we are starting another session of the Transcarpathian seminar on geometry and physics. Our pleasure today is to listen to our friend and collaborator Witold Respondek, who will be teaching us about control theory, especially about linearization of mechanical control systems. The talk is planned for 2 times 45 minutes with a break roughly in the middle. However, the precise position of the break is up to you, Vitek. When you decide that this is the right place for us to stop, please do. And the stage is yours.
Thank you very much, Kasia, for a very nice introduction, and thank you very much for your kind invitation. It's my pleasure and my honor to talk for your Transcarpathian seminar, and I would like to tell you how geometry helps to state and then to solve the problem of linearization of mechanical control systems. So all what I'm going to tell you today is based on joint research with Marcin Nowicki from Poznań. So throughout, I will be talking about the following problem. When is the mechanical control system of that form equivalent to a linear mechanical control system? So what is my mechanical control system? X are positions, configurations, Y are velocities, gamma is quadratic with respect to velocities, and U is a control. And I want this system to be equivalent to a linear mechanical control system of that form. So in order to be precise, I have to justify why this is my choice of mechanical control systems, why this is a natural linear mechanical control system, and the most important, what I mean by those two to be equivalent to each other. So,
excuse me, you mean that your E, etc. are constants?
Script E is not, capital E, yes, but I will be more precise in a minute. This is just a very rough statement of the problem. So in the system above, all depends on X, on configurations. In the system below, nothing depends neither on X, nor on Y, nor on U. Does it answer your question?
Well, I just wanted to know if E and B depend on something or no.
Capital E and capital B do not depend on anything. In my problem, you may consider a time-varying version, and then E and B will be time-varying matrices. But for me, both will be constant.
Okay.
So the plan of the talk is as follows. I will start with defining mechanical control systems and justify my choice. Then I will define two equivalence relations for them, state space equivalence and feedback equivalence. And for both of them, I will formulate the problem of linearization and mechanical linearization. Then I will state our main result, which is formed by necessary and sufficient conditions that guarantee that a nonlinear system is equivalent to a linear one. In the first part, I will assume that the linear control system is controllable. Then in the second part, I will drop that assumption. And finally, I will end up with conclusions. So since not everybody knows what are control systems, I would like to advertise them. And actually, we can look at control systems at 3 different ways. So the first way is the following. A control system is a time-varying differential equation. So this equation evolves on the state space, which I will denote Z, which is d-dimensional, d as dimension. And there is a time-varying function U, which is control. Yu because the first book written on control was that about optimal control written by Pontryagin, Bołciański, Gamkrelidze, and Miszczenko, and control in Russian is upravlение. So that's the historical reason for which controls are always denoted by U. And then what is important to understand is that I don't fix a particular U of t. I have a choice. So in order to solve this equation, I fix an initial condition and I have to choose a control. There are as many solutions as possible choices of my control. Okay, so that's one way of thinking about a control system. Another way is, although clearly in this first equation, the variables z and the variables u are of different nature, because z enter in a differential way into the equation, and there are no constraints on u, neither static nor dynamic, I will forget those differences. I will say, how many variables do I have in that system? Clearly, since dimension is d, so there are dz variables. So I will introduce wi, which are the first d variables, zi, and then the other mw variables, wd plus 1 up to wd plus m, are control variables. So I denote all variables that are present here, as well z variables as u variables, by w. And then I rewrite this equation in the following way. It's a system of d scalar equations, wi dot equals fi, for d plus m variables, because there is d, z variables, and m, u variables. So this system is an underdetermined system of differential equations. There is more variables, d plus m, than equations, d scalar equations. So underdeterminacy means that some variables are completely free, and those are controls, no constraints put on them. And then the third possible way is to look at this control system geometrically. Namely, geometrically, this is a differential inclusion. Z dot, the velocity, belongs to f. What is f at zu? At each point z, I take all possible values of the right-hand side. That means I take all values of u, and under the natural assumption that f is an embedding and that the rank is full, in each tangent space, I am given an m-dimensional submanifold of the tangent space. So actually, this differential equation is the differential inclusion given by a collection of m-dimensional submanifolds. Okay? Now, those submanifolds can be as simple as possible. In particular, there can be just subspaces. So a particular example is a Pfaffian equation. I am given k differential forms, omega j, one forms, and I consider the Pfaffian system given by omega j equals to 0. There is k of them. Okay, so the integral curve satisfies this equation if omega applied to its velocity is 0. And here I use only z variables. I can rewrite it in a way that is analogous to what I told you about here. Namely, the velocity z belongs to g, script g. What is script g? Is the distribution that is spanned by m vector fields. Why m? Because my dimension was d. There is k independent equations, so m is the difference between the dimension d and the number of equation k. So at least locally I can span this distribution by m vector fields, and I can rewrite this Pfaffian equation as z dot belongs to the distribution g. But if I want to write down differential curves, then I have to introduce controls. Namely, differential curves are given as solutions of this control system. Since my submanifolds in each tangent space are just subspaces of dimension m, then this equation is linear with respect to controls. So once again, controls are unavoidable if I want to write down explicitly solutions of my system. I may not use them if I write in this form, but if I want explicitly write down solutions, then controls appear naturally as coefficients multiplying the vector field gi. Gi span the distribution G, which is simply the kernel of this RK valued differential form omega. Okay, so control systems can be linear if controls enter linearly. That means in each subspace of the tangent space we are given a subspace, or very often, and actually throughout my talk, they will be control affine. That means the control enters in an affine way. Meaning what? Meaning that if I don't control the system, if I put all controls ui equal to 0, then it's the vector field f called the drift that is telling me what is the evolution. But if I control, I use use. So the set of all admissible velocities, that means the set of all values of the right-hand side, is an affine distribution this time. What is it? I take the vector fields g1, gm, I span the distribution G using them, and I add to that distribution a vector field F, the drift. So at each point, I have an affine subspace of the tangent space given by the drift plus the distribution spanned by controlled vector fields. The matrix G consists of columns G1, Gm, which are the control vector fields. Okay? So knowing that, I can define precisely what I mean by equivalence. So I consider two control systems, control affine, both. Once again, that's enough for my talk. And I will say that those two systems are state space equivalent, which I will shortly denote by S equivalence, if they have the same controls. So the controls U, there is M of them, and controls U tilde, once again, M of them are the same, and there exists a diffeomorphism that maps the drift of the first system into the drift of the second system, and this same diffeomorphism maps the control vector fields, Gi, there is M of them, M columns of the matrix G, into the corresponding control vector fields of the second system. So once again, I want the same diffeomorphism to do the job, to map the drift into the drift and the control vector fields into the control vector fields. Okay? And this diffeomorphism acts via the tangent map on my vector fields. That's one equivalence relation. And another, feedback equivalence, which I will shortly denote F equivalence, means that there exists a diffeomorphism phi that maps the affine distribution F plus G, corresponding to the first system, into the affine distribution defined by the second system. Okay? So this is purely geometric. I forget about particular control parametrization of my system. Given a system, I attach to it its affine distribution. In other words, the set of all admissible velocities. And I want the set of all admissible velocities to be mapped into the set of all admissible velocities of the second system.
These states need not to be United States.
It's not to be United States, and state equivalence does not include neither Canada nor Greenland. Now, why those two equivalence relations are natural?
Does it include Panama?
Still not yet.
Not yet.
Why are those two equivalents natural? The first means simply the following property. Two systems are state space equivalent if and only if there exists a diffeomorphism that maps trajectories into trajectories. Okay? Now, what about feedback equivalence? I mean, feedback equivalence reparametrizes trajectories. To be more precise, either we use this geometric definition where we get rid of controls, or if for some reasons this control representation is important for us, we can rephrase feedback equivalence as follows. Two systems are feedback equivalent if and only if there exists a diffeomorphism phi, and two smooth functions, alpha, that is, are m-valued, m is the number of controls, and beta, whose values are in the group of invertible matrices, such that if I take the drift of the first system, I can add to it any smooth combination of the control vector fields, and I transform by my diffeomorphism this modified drift, and I want to get the drift of the second system. And I can take smooth combinations of the control vector fields among them, and then those smooth combinations are mapped by the diffeomorphism into the vector fields of the other. Meaning what? Meaning that feedback equivalence also preserves trajectories, but attention, preserves the totality of all trajectories, but reparameterizes them with respect to controls. So two systems that are feedback equivalent, they have the same trajectories, but parameterized differently with respect to control. So the two are equivalent, and clearly, I mean, the feedback equivalent is weaker, that one is the stronger. Here I want the vector fields to be preserved. Here I want the affine distribution to be preserved. Okay, so if we know what is equivalence of our control systems, I will tell you what I mean by mechanical control systems. So a mechanical control system with n degrees of freedom and m controls is a four-tuple that consists of a configuration manifold of dimension n, a symmetric affine connection on Q, an m-tuple of vector fields on Q, G1, Gm, which are controlled vector fields, and one uncontrolled vector field on Q as well. Okay? So the small letters G, 1, Gm, and E correspond to objects that are on the original configuration manifold Q. And capital letters would correspond to objects that are on the tangent bundle. You will see that many times throughout the talk. A curve is a trajectory of my control system if it satisfies the following equation. So the covariant derivative of x dot with respect to x dot, which is the intrinsic acceleration, the geometric acceleration of my system, equals to the right-hand side. So this equation is actually a balance of accelerations. What we are given on the left-hand side is the geometric acceleration, the acceleration that is given by the geometry of Q, equipped with an affine connection. And what is on the right-hand side is the acceleration given by an external action that is uncontrolled due to E and controlled through use thanks to the vector fields GR, okay? And those two accelerations have to coincide. I mean, for this affine connection, the covariant derivative is the usual one defined with the help of Christoffel symbols. So in other words, my mechanical control system is a second order differential equation on Q given by that formula. That's the acceleration, and that's the action of external that's the external action, uncontrolled and controlled. Geometrically, the Christoffel symbols of the affine connection correspond to the Coriolis and centrifugal forces. And the vector fields E and G correspond respectively to the, as I said, uncontrolled action and control action. A comment, our class is a bit more general than simple mechanical control systems, as studied by Francesco Bullo and Andrew Lewis in their beautiful book. It's more general because once our connection need not be a metric connection. It can be if a Riemann metric is given, then it will be the Levi-Civita connection, but it can be any connection, not necessarily metric. And secondly, the uncontrolled vector field can be any. It need not be potential. Okay. Now, equivalently, this control system is a first order differential equation on the cotangent bundle. So first half of equations are, derivatives of positions are velocities, and derivatives of velocities, accelerations, are given by that equation. Now, just a comment. You know it as well as I do, but I like this example because it's showing why I need to use an affine connection. Just take as a point that is rotating on R2 along a circle. So that's the curve. That's the velocity. So it's perfectly correct. It's tangent to the circle. And that's the acceleration, which points towards the center. So all is perfect. Now, if I pass to polar coordinates, then the radius does not change. The angle is t modulo 2 pi. Then the velocity is 0, 1. R does not change, so it's 0. The angular velocity is 1, so it's perfect. But the acceleration is 0, 0, which is clearly not correct. I need an affine connection. In other words, as everybody knows, the second order derivatives are not geometric. To become geometric, we need an extra structure, which is the affine connection. Now,
can I ask a question?
Sure.
No, because of course, you can make sense of second order derivatives as a geometric object if you work, if you do not insist that those second derivatives are just elements, if they are not, if they are not a vector, yeah? So the second derivative is an element of the second tangent bundle. You can put it all inside the iterated tangent bundle. So is it possible to formulate this all on a tangent bundle using, I don't know, the concept of a spray or whatever, and not introducing the connection? So is connection essential, or is it just a tool to write it down conveniently to be able to detach the acceleration from the point when it is attached? Yes.
I think it's essential because if you use the geodesic spray, you introduce Christoffel symbols which define a connection. So you may not say that Christoffel symbols define a connection. You may say those are just functions that are quadratic with respect to velocities, but if you introduce them, that means you introduce a connection.
No, yes, you introduce a spray in a sense when it is quite. Maybe I am not using the terminology correctly. But you can
semi-spray.
Yeah, semi-spray. Yes,
Semi-spray,
you can just use a second order, the first order representation of the second order vector field. Yeah. So something that is a section of the second tangent bundle represented as embedded in the iterated tangent bundle. And does it make sense? Maybe it doesn't. Maybe you really need the connection.
Yeah, the point is the second tangent bundle is not a vector bundle.
Yeah, it is okay, but it's
and the question, why do we need an affine connection? No, we need it to prove the theorem.
No, I think we need it. Physically, the acceleration is a vector, so we need it to define a vector object that measures how the velocity changes.
No, physically it's not a vector because geometrically it's not a vector. Only in fixed coordinates this you can interpret this as a vector. But of course this is not a geometrical notion.
I don't share your point of view. If you introduce a connection, you are able to attach a vector nature to the acceleration. That's the covariant derivative, which is a vector.
But the same is with velocity. You cannot detach velocity from the point.
Yes, nevertheless, it is a vector.
Yes.
And then it's not a free vector. It's just a vector attached to a point. The same with the acceleration. It is
No, not
attached
the
to.
same with the acceleration. The acceleration is not a vector. It's a section
Yes,
affine
but it,
of
because it is attached to
not
the
only
velocity.
it does not transform linearly, it transforms affinely. So it is. I mean, there are two problems. You cannot detach
Yes.
it, and it is not a vector.
No, actually, this is not acceleration which makes sense. The second jet of a curve makes
Second jet.
sense.
Yes.
Of course, the particular coordinate of the second jet in given coordinate system, you can call acceleration, but it doesn't make vectorial sense.
No. So I want the acceleration to has a vectorial sense, and for this reason I need the acceleration. I need the connection, because when I covariantly differentiate the velocity along x dot, I will get a vector, and that's the acceleration. I mean,
of course, if you have a connection, everything is possible.
Yeah. So in this equation, I want to compare two vectors, and so I want.
But this is why you need a connection. But the question of Kasia is, if I understand properly, whether you can don't use connection and use the second jet instead.
I don't think so, because I want this to transform correctly when I change coordinates.
If I can make a remark, so I
Sure.
think the answer to Kasia's answer is yes, you can do this, but you will have to require this affine. You have to somehow lift this affine distribution on the right hand side to something that satisfies the double. It's a distribution that has to consist of double tangent vectors. So it means that its sections would have to be semi-spaced. So if you want to do what Kasia is suggesting, you can go to the double tangent bundle, but you need this involutivity, right? That is involution of the double tangent bundle, which exchanges the two vector bundle structures. And you will
you
need
probably
the
need
lift
some
to be
additional structure here.
to be invariant under that involution. Some additional condition, not some additional structure.
Okay.
So yeah.
Okay.
I have a remark that in general relativity, everybody says acceleration with a connection. So because the connection is in the theory. So this nabla x dot is a for relativity people it's an acceleration. For mechanics it's different. Yeah.
Okay. Thank you for your questions and remarks. So I am ready to start stating result about state space linearization. So forget for a moment that my system was mechanical. I'm just taking a general control affine system whose state space is TQ, the tangent bundle. And I will say that it's locally S-linearizable if it is state space equivalent, S equivalent to a linear control system of this form. So answering to the question of Janusz from the beginning of my talk, A and B are constant matrices of appropriate dimension. Okay. So I want, in other words, the diffeomorphism to map F into a linear vector field, and the same diffeomorphism should map the columns of G into the constant columns of B. And it's a classical result of geometric control theory that a nonlinear system is equivalent to a linear controllable system if and only if the following rank condition is satisfied. So I take the vector fields Gi, the columns of G, and their successive brackets with F, and they should span the whole tangent space. The dimension of my system is 2n. And the condition, the true geometric condition, is this one. Any Lie bracket that involves two G's, that means RFGJ, R, RFGIQ, have to vanish. So if brackets that involve two G's vanish, then of course all brackets that involve more G's vanish as well. So the only non-zero Lie brackets are of that form, and they have to span the whole tangent space. By controllability, I mean that this linear system is controllable, meaning that given any initial and final condition in its state space, Rd, I can find a suitable control that steers the initial condition into the final condition, the terminal condition. And that's if and only if the matrix whose columns are those of B, then those of AB, and so on up to A, D minus 1, is of maximal rank D. Okay? So this is a known classical result. And now, as I told you, for a moment, I decided to forget that my system is mechanical, but now I recall it. It was a mechanical system. So the question that is very natural is that since MS is mechanical, so if it is state space linearizable, that means I can bring it to a linear form, is it possible to do both at the same time? That means, does the linearizing diffeomorphism preserve the mechanical structure? This diffeomorphism maps a nonlinear system into a linear one. Does it preserve its mechanical structure? Or in other words, are the two structures, mechanical and linear, compatible? Okay? And this is the question I would like to study. So to be more precise, what I mean by a linear mechanical control system, so it has to be at the same time linear and mechanical. So it's mechanical, the derivatives of positions are velocities, here are accelerations. So here the matrix A is 0, identity E 0, B is 0, B, and observe that I added a constant vector field C to it. Why? Because I'm interested in linear control systems at equilibria, where C is not necessary, but also at non-equilibrium points. And if I do that, if I shift a non-equilibrium x0 into 0, then I will produce this term, this constant term C, which is simply E times x0. So this is a linear mechanical control system I'm interested in. And my goal is to describe such systems. So I can associate to this linear mechanical control system a particular choice of 4 tuple, namely its configuration manifold is Rn, its connection is flat, that means Christoffel symbols vanish, the m tuple of control vector fields are just columns of B, so constant vector fields, and the drift is an affine vector field. Now, in order to be able to answer the question, is it possible to do simultaneously both, to linearize and to preserve the mechanical structure? I will say that a mechanical control system is mechanical state space linearizable, shortly MS linearizable, if the diffeomorphism that maps this system into its linear equivalent is of a special form, namely the positions depend on positions only, and the velocities are mapped by the tangent map. In other words, I use extended point transformations. My diffeomorphism is not the most general one. It respects the bundle structure of the state space of the system. Okay? In other words, my nonlinear system evolves on the tangent bundle. My linear system on the tangent bundle of Rn, that means on R2n. And if I talk about state space equivalence, I can apply any diffeomorphism of this state space into that state space. Now, for mechanical diffeomorphism, I want the configuration manifold to be preserved. That means positions, new positions x tilde depend on original positions only, while velocities are mapped by the tangent map. So what do I want? I mean, this is my mechanical system. Its drift is this geodesic semi-spray plus the uncontrolled vector field. The controlled vector field are capital G's, and look that capital G's are vertical lifts of small g's, okay? And I want the same diffeomorphism to map this mechanical drift into the linear mechanical drift, velocities, accelerations, and the control vector fields into constant control vector fields. Now, this is happening in the tangent bundle, but of course I may reformulate that in terms of objects living on the configuration manifold only. Namely, a mechanical system is mechanically state space linearizable via the diffeomorphism that is an extended point transformation, if and only if the diffeomorphism just in the configuration manifold, small phi acts in the configuration manifold, capital phi in the tangent bundle, maps the small drift into the linear drift, the control vector fields into constant vector field, and the transformed connection is flat, whereby phi of nabla, I mean the transformed connection. Okay. So what about trajectories? So of course, this small diffeomorphism trajectories into configuration manifold into trajectories of the configuration manifold. The capital diffeomorphism trajectories in the tangent bundle into the trajectories of the tangent bundle. And of course, the diagram is commutative. Observe that the trajectory in the configuration manifold depends not only on the point at the configuration manifold, but on the whole z0, that means on velocities as well, right? There are as many trajectories as possible velocities at x0 and possible controls that are applied. So here is the first result that I would like to present you. A mechanical control system is locally around a point in the configuration manifold, MS linearizable to a linear controllable mechanical system if and only if the following three conditions are satisfied. So I will start with those two. Look, we know them because they are just state space linearizability conditions for the virtual system. This is not my mechanical system. This system evolves on the configuration manifold, and actually I have to take the vertical lift of E and vertical lifts of G's to get my mechanical system. So those two conditions guarantee that this vertical system is S-linearizable. That means there exists a diffeomorphism in the configuration manifold that maps this system into a linear system. And now, what is this condition? This condition means that the symmetric brackets vanish. Look, here are Lie brackets, and they are responsible for linearizability of this. The symmetric bracket of two vector fields is the covariant derivative of y with respect to x plus the covariant derivative of x with respect to y. I think it was introduced by Peter Crouch. And all symmetric brackets have to vanish. And they are responsible for the fact that if I linearize this virtual system, in the linearizing coordinates, the connection is flat. That means the Christoffel symbols vanish. That's the role of those symmetric brackets conditions. Now, it is surprising that it's not that far to go from a local result to a global one. Look, this result is local, around a point in the configuration manifold. Now, a mechanical control system on the tangent bundle is globally mechanically equivalent, MS, there's M missing here, MS equivalent to a controllable linear mechanical system. It's a global system, so it evolves on R to N, if and only if it satisfies those three conditions that we have just seen, plus two extra conditions. The first condition is that the vector fields E, G1, Gm are complete oh, I wrote F instead of E, excuse me. Equivalently, the successive Lie brackets of GI with E are complete. That's a famous theorem by Palais that if generators of a finite dimensional Lie algebra are complete, then the whole Lie algebra is complete. By completeness, I mean, of course, that the solutions of the corresponding differential equations exist for all positive and negative T, and that the manifold Q is simply connected, not X, but Q is simply connected. If I drop this assumption, I will still get a global system, but which does not evolve, whose configuration space is not Rn, but it's a k-dimensional torus times n minus k. Okay? So it's surprisingly easy to go from local results to global results in the case of S equivalence, state space equivalence. We will see the difference with feedback equivalent. Now, I will pass to feedback linearization, so the second equivalence relation. And once again, like I did for state space equivalence, I forget for a moment the mechanical structure of my system. I just consider it as a control system, control affine. Then it's a classical result of geometric control theory due to Bronek, Jakubczyk, and myself, and independently to Hunt and Su, that locally you can transform this nonlinear system into a linear one if and only if the two following conditions are satisfied. You form the distributions dj that are spanned by successive Lie brackets of gi. Gi are control vector fields with f up to j, and those distributions have to be of constant rank and involutive for all j between 0 and 2n minus 1, and the last one, 2n minus 1, we are on the state space of dimension 2n, has to be the whole tangent bundle. So the geometry of feedback linearizable systems is like this. Successive Lie brackets of the control vector field gi with f define a nested sequence of distributions. All those distributions, d0 is just spanned by g's, d1 by g's and their brackets with f, and so on. So all of them, they have to be of constant rank. All of them have to be involutive. And then the last one has to be the whole tangent space. Okay? So we have an analogous question to the one that we already discussed for state space linearization. Do the linearizing transformations, and now what are they? A diffeomorphism and a feedback transformation, and a affine transformation that changes the drift and the control vector fields, preserve the mechanical structure. Or in other words, there is this linear structure that is encoded by the sequence of involutive distributions, and there is the mechanical structure. Are they compatible? Okay, so we have to say what we mean by mechanical feedback transformations. It's natural. The group of mechanical feedback transformations is generated by mechanical diffeomorphism or mechanical changes of coordinates. So those we know quite well. Positions are mapped into positions, velocities into velocities via the tangent map. Plus now we have feedback transformations. Since our system is quadratic with respect to velocities, then feedback transformations are also quadratic with respect to velocities, with coefficients that depend on configurations only. Okay? And the definition is, I will say that a mechanical system is feedback linearizable, shortly MF linearizable, if it is MF equivalent in this sense to a linear mechanical system. That means if there exists a transformation that is a diffeomorphism and a control reparameterization of changing of generators f and g's, if you prefer, that map the given mechanical control system into a linear mechanical control system. So I think it's a good moment to make a break. Are there any other questions to the first part, except those that have been already asked?
I don't have a question. Actually, I have to express some hope that you are going to present an example because I got a little bit lost at some point.
Of course, they will be examples. But if you
Fantastic.
are lost, tell me when and why, and I will try to.
No. But this is I cannot point a specific parts of your presentation when I got lost. I just got overwhelmed by a number of definitions. But this is probably unavoidable. That's why I hope for an example, because then you can somehow sort yourself out and attach more meaning to the definition. Okay, so I suppose that it's time for a break. Let's meet at 3:15. Time for coffee, tea, or whatever. Unfortunately, we are not serving cakes today.
Or as Andrzej Sapkowski, the writer, used to say, he will put some powder on his nose.
Yeah.
You should have told that you have cakes and help yourself.
As a matter of fact, we do, because we have today a guest from abroad and we try to be polite. Therefore, we have cakes and we are going to eat them.
Okay.
And I think we can continue. Witek, you are muted.
Okay.
Yes, now we can hear you.
Now, is it fine?
Yes, now it is okay.
Okay, good. So let us restart. And since Kasia made a confession that she was lost, let me make a very short resume of what we learned and what we should remember for the second part. So the first message is, I am dealing with control systems that are affine with respect to controls, that means of that form. And I consider two equivalence relations. State space equivalence, meaning that I want a diffeomorphism to map the control vector fields into control vector fields and the drift into the drift. And another, weaker, more general, I want the distribution spanned by G's to be mapped into the distribution spanned by G's, and the drift into the drift modulo the distribution G. In other words, the affine distribution into the affine distribution. Okay. And I'm not studying the problem of equivalence of general systems of that form, but what I am interested in are mechanical systems of that form. And I want such a mechanical system to be equivalent to a mechanical linear control system. So this is my problem throughout. When is such a control system, this one, either S equivalent or F equivalent, either state space or feedback equivalent, to a linear control system of that form. Okay, and what I am using are mechanical transformations because I want linear and mechanical structures to be compatible. So my diffeomorphism is not the most general one of that form. I want positions to depend on positions and velocities on velocities via the tangent map. And feedback transformations, since my mechanical control system is quadratic with respect to velocities, I want it also to be quadratic with respect to velocities. Okay, so just before the break, I defined it mechanical feedback transformations, which are once again mechanical diffeomorphisms, if you prefer extended point transformations, and transformations of control that preserve the mechanical structure of the system. Why is this natural? Because once again, maps configurations into configurations, velocities into velocities via the tangent map, external forces, independently whether they are controlled or not, whether they are potential or not, are mapped into external forces, and accelerations are mapped into accelerations. In other words, feedback linearization, mechanical feedback linearization, preserves all physical properties of the system. General feedback linearization may not. And here is an example showing what can happen. So consider the following mechanical system. Kasia asked for an example, so I dedicate it to her. There are two positions, x1, x2. There are two velocities, y1, y2. There is one control that controls the second velocity. And the system is nonlinear because of this Christoffel symbol x2. There's this quadratic term with respect to y1. The first question is this system at least locally feedback linearizable? There are two ways. We can either check linearizability conditions. I recall you that's this sequence of distribution. So you can see that the first that is spent by this direction is involutive, the second by those two involutive, the third by those three involutive. So it is. But actually for this example, we can explicitly find linearizing coordinates, namely the following transformations linearize the system. What are they? But we don't change the first position. We don't change the first velocity. We replace the second position by that expression and the second velocity by that. And if you calculate the transformation of controls, it is like that. Those transformations map this mechanical system into that mechanical system, which is mechanical. The derivative of the first new position is the new velocity. The derivative of the second new position is the second new velocity. The control appears at the end. So the system is mechanical and linear. It's just a chain of four integrators. Okay? But the transformations that we have just calculated are not mechanical. Why? Because new positions do not depend on original positions only, but also on velocities. So this diffeomorphism, together with that feedback transformation, maps a mechanical nonlinear system into a mechanical linear system. So they linearize. Those are linearizing transformations, but they are not mechanical. They don't preserve the mechanical structure. They mix up positions and velocities. Question, can we linearize this system better? Can we linearize it in such a way that the mechanical structure is preserved? So to formulate the result, let us assume that M is one, only one control for simplicity. Consider this virtual system that we already know. It's a system evolving on the original configuration manifold, and we will attach to it linearizability distribution, the distribution that we know. So E0 is spent by G, E1 by G and the bracket with E, and so on. So in order that this system is linearizable, all of them have to be involutive and of constant rank. And I will also need the second covariant derivative, not the first one, which I already used. The second covariant derivative of a vector field Z with respect to xy is given by that formula. That's the standard second covariant derivative. And here is our result that holds for systems with at least 3 degrees of freedom. I will discuss the case of 2 degrees of freedom in a moment. And the result says that a mechanical control system is locally, mechanically linearizable if and only if the four following conditions are satisfied. So the first two simply mean that this virtual system is feedback linearizable. And then we have two more conditions. The first is that if you calculate the covariant derivative of G is the only control vector field, then the covariant derivative are always in E0. E0 is the first distribution, the one spanned by G. That means if we calculate the covariant derivative of G, we stay in the space that is spanned by G independently of the direction in which we calculate the covariant derivative. Those vector fields at EGI, for I between 0 and n-1, they are independent. So actually we take those derivatives in all n directions, and all of them have to be collinear with G. And then the second condition is speaking about E, the drift, the second covariant derivative. E, we want it to be linear, so it's not surprising that there is a condition that involves second derivative. We want this, roughly speaking, that the second derivative is 0, because we want this to be linear in well-chosen coordinates. And it's true, the second covariant derivative in all those directions has to be in E1, which is the second involutive distribution. This one, E1, is spanned by G and at EG, okay? So as I said, those two conditions, we understand them very well. They guarantee that the virtual system is feedback linearizable. And then those two guarantee that if I take coordinates and feedback that linearize the system, I will find among them one coordinate system in which Christoffel symbols vanish. Okay, that's the role of that condition. And the role of this one is that G will be constant, perhaps multiplied by a function. Okay, so those are the conditions that guarantee that I can feedback linearize mechanically a system. That means I will be able, if those conditions are satisfied, not only to linearize it, but to linearize it and to preserve at the same time its mechanical structure. As I said, the above theorem does not work for systems with 2 degrees of freedom, for the very simple reason there is not enough space there in order that the conditions work. They become trivial. Let me come back to them. Look, this condition means that all distributions should be involutive and of constant rank, but there's only one non-trivial distribution, which is E0, if n is 2. And E0 is always involutive because it's of rank 1. This condition is trivially satisfied as well, because E1 is spanned by G at Fg, but for 2 degrees of freedom, G at Fg are independent because of that. So this condition means that we are in the tangent bundle with those derivatives. So in order to get a condition, we have to replace those two conditions that are trivially satisfied, MF2 and MF4. They are absent in the statement because, as I have just explained, they are trivially satisfied, and they are replaced by that condition, namely the commutator of the second derivative. So in both derivatives, I calculate the covariant derivative, the second covariant derivative of this vector field, but here in the order G at EG, and here in the order at EG, G. This difference has to be in the only non-trivial distribution, which is E0. The only non-trivial, because once again, E0 is of rank 1, and we are in dimension 2. Okay, so what I would like to comment is first that the conditions of the first theorem, MF1, MF4, those conditions, as well as the conditions in the case of 2 degrees of freedom, they are checkable via differentiation and algebraic operations only, so no need to solve PDEs, no need to bring a system to a normal form. So, I mean, we can check it. I mean, our computer can check it. Our children can check it, whoever. Second, we can apply this theorem to example 1, right? So for that example, let me recall it very briefly. It's this one. So M is 1 control, N is 2 degrees of freedom. So the second, this one, theorem applies. And what we get is G is d over dx2. Its bracket is this one. So conditions for involutivity is satisfied. We calculate the covariant derivatives. This one is 0. That one is 0 as well. So they are in E0. But the difference of the second covariant derivatives is that vector field, which is not in E0. E0 is spanned by G. That means by this vector field. So this system is not mechanical feedback linearizable, although, as we proved by a direct calculation, it is feedback linearizable. So this shows what we could have expected, that feedback linearizability is less restrictive than mechanical feedback linearizability. I mean, the latter requires both linearization and conservation of the mechanical structure. So if we have a system like that of example 1, which is F linearizable but not mechanical feedback linearizable, then for such systems, mechanical and linear structures are not compatible. So given such a system, we have to choose. Either its mechanical structure is very important for us, so we keep it, but then we have to give up the linearization, or linearization is important for us, so we linearize, but then we pay a price. The price is we lost its mechanical structure. You wanted an example? Here you are. So let us take this system. It's a system of two masses, M1, M2, two springs, K1, K2, and there is a pendulum attached to the second mass. There is the gravitational acceleration. The moment of inertia of the pendulum is J3, and the masses are respectively M1, M2, and M3 of the pendulum. So there are 3 degrees of freedom. For instance, the position of the first car, the position of the second car, and the angle of the pendulum. So it's called the Tora system, translational oscillator with rotational actuator. And we added gravitational effects to it. We take into account the gravitation. So as I said, there are 2 masses, M1 and 2, 2 spring constants. That's the mass of the pendulum, the moment of inertia. And there is one control, that's the torque U here that is applied to the pendulum. So the kinetic energy, or the metric, is this one. So it's not Euclidean because of that term. That's the product of the second and third velocities. So the Riemannian metric is not Euclidean, but it becomes Euclidean in well-chosen coordinates. And then condition MF1, MF4 are satisfied for this system, and the system is mechanical feedback linearizable. So this system, you can linearize, and more than that, you can linearize it in such a way that you preserve its mechanical structure.
But what is control here?
It's the torque.
Ah.
You apply a torque to the pendulum. You see, so if you apply this torque, you move the second car, and because of the spring, you move also the first car. Okay? So there is 3 degrees of freedom and 1.
Okay.
Okay? Now, what I would like to discuss now is the following observation. In all results that I have presented, both for state space linearization and F-linearization, we wanted the nonlinear system to be equivalent, either just by change of coordinates or by feedback, to a linear mechanical controllable system, okay? Which makes things easier. Why? Because, as we discussed many times, this is the condition that is responsible for controllability. This is the condition that is responsible for the controllability. In other words, those vector fields at GEI, I between 0 and n-1, are independent. So they define a frame. And it's much easier to check other conditions given a frame. We don't change this frame if we work with state space equivalence. We modify it by feedback if we apply feedback equivalence. But the fact that they form a frame is preserved by feedback. So it makes things simpler. So a natural question is, can we drop that controllability assumption and obtain results that guarantee state space linearizability or feedback linearizability in the mechanical sense without controllability assumption?
Excuse me, there is
Yes.
a question.
Sure.
So I had an impression that this controllability is kind of geometric property of the system, not something that depends on chosen coordinates, but something which is geometric. And now it seems it isn't. So was I wrong in the beginning?
No, you were right from the beginning. It is a geometric property of a linear system. I mean, linear system, it's a global system on Rn. And then, as I said, it's controllable if and only if you can go from any point to any point. Now, since many of our results were local, then what is local controllability? So local controllability means that the set of points to which you can steer your system contains an open subset. Since you work locally, for instance, drift can push you, then you will not go to any point because of the drift, but still the set of points to which you can steer has to be huge, has to contain an open subset. And for a linear system, if your system is on the whole Rn, the fact that you can steer to an open subset, if you steer on the whole Rn, you can steer everywhere. That's a property of linear systems. But it's independent on coordinates. It simply means that the successive Lie brackets, iterative Lie brackets of your system form at each space the whole tangent space. For linearizable systems, those are only brackets which contain one G, because brackets that contain more than one G have to vanish.
But what you say refers only to affine controls?
No. What concerns S-linearization, yes, because S-linearization cannot change the fact that you are affine with respect to controls, because you act with your diffeomorphism on the right-hand side. So if your right-hand side is not affine with respect to controls, it will not be after applying a diffeomorphism. So if you want to linearize a system using a diffeomorphism only, your system from the very beginning has to be control affine. On the other hand, if you want to linearize a system that is not control affine by feedback, you may do it. And then there is a very elegant result saying the following. You take a system with controls entering in any way you wish, a nonlinear way. You take its first prolongation, which is, you say, I don't control U's, I control their derivatives. So that means you add to your system the M equations UI dot equals VI. You are following me? You say U's are part of my system. Okay, I'll go to the beginning. Yeah. You take this system and you write down U dot equals V, telling V is my control. So with respect to V, this extended system, the first prolongation of this system is control affine. And this nonlinear system, nonlinear with respect to U, is feedback linearizable if and only if its extension is feedback linearizable, but its extension is control affine with respect to the new control V. So actually all that was said about control affine systems can be extended to systems that are nonlinear with respect to controls by this very, simple but elegant trick. Does it answer your question? Janusz?
Yeah, thank you.
You are welcome. Okay, so as I said, till now I wanted my linear system to be controllable. And that made things a little bit easier because controllability guarantees the existence of a frame. I would like to drop that assumption. And in order to do that, I will need the Riemann tensor, which, as you know, that's seminar on geometry and physics, was introduced by Bernhard Riemann in his habilitation talk in 1854. And in my opinion, by far, that was the best habilitation ever in the history of humanity. So, and actually it was by accident, because as you know, in the classical German system, you were supposed to prepare a habilitation talk not on the subject you were specialized in. You had to prepare 3 talks on 3 different subjects, none of them related to your scientific interest. And then the commission decided which of those 3 will be given. And then one of them that Riemann prepared was about geometry. And then the committee asked him to give that talk on the geometry. And in that talk, he introduced the Riemann tensor, which is defined, as everybody knows, as follows. That's the commutator of covariant derivatives, which can be written in local coordinates in that form, or if you want to calculate using the Christoffel symbols and their derivatives. Okay, so for a connection, let us denote by nabla f the total covariant derivative of a vector field, and by r the just defined Riemann tensor. So for state space equivalence, mechanical state space equivalence, we have the following result. A mechanical control system is locally mechanically linearizable to a linear system that I want to be mechanical, as you know, but I don't care whether it's controllable or not. I just want my nonlinear system to be mapped into a linear mechanical control system, and that's the case locally, if and only if the following conditions are satisfied. But the Riemann tensor is 0, the total covariant derivative of control vector fields is 0, and the second total covariant derivative of the drift is 0. So in a sense, that's very natural result. That's what you would expect. Why? Because r equals to 0 guarantees that there exist coordinates in which you can get rid of Christoffel symbols. So there will not be quadratic terms in your system. Now you want in the same coordinates the control vector fields to be constant. So they are covariantly constant, and you want the drift. That's the only part of the drift, because in the coordinates in which your connection is flat, there are no Christoffel symbols. So the only part of the drift is E. And then the second covariant derivative is 0, meaning that implying that E is linear, or affine if you work out of equilibria. So I mean the importance of that Riemann tensor being 0 was observed already by Mark Spong, Bedrosian, and Kodicek. Excuse me. Now those conditions show that that's the compatibility that we needed. In other words, in the coordinates in which you get rid of Christoffel symbols, the control vector fields will become constant and the drift will become linear.
I must say that this theorem makes me happy, because I was uneasy because of the lack of the condition of vanishing Riemann tensor.
Mm-hmm. So yeah, so that's, yeah, it's sort of a natural. And now the question, okay, you can get also a global result, but that's a little bit more difficult, because actually the fact that we could have for state space equivalence global result was due to the existence of that frame. Here if your linear system, if your linear equivalent is not controllable, you will not get a frame. And what is more difficult is to understand what is happening with this condition when you apply feedback. Okay, and that's what I would like to discuss now. So I need 4 annihilators. Lambda is the set of smooth one forms on Q. So the annihilator of E0 are all forms that annihilate GR. GR are control vector fields. In other words, I recall you, those are vector fields, they simply span the distribution E0. Annihilator of R are forms that annihilate R. The annihilator of total covariant derivative of GR are forms that annihilate that. And the annihilator of the second are forms that annihilate the second. Okay. So although those objects, a distribution, the Riemann tensor, the total covariant derivative, the second total covariant derivative, are of different nature, their annihilators in all 4 cases are simply one forms. And then our theorem is telling us that a mechanical system is locally mechanical feedback linearizable if and only if it satisfies in a neighborhood of x0 the following condition. 2 first distributions are of constant rank. Only the first needs to be involutive. Actually, all have to be involutive, but due to next conditions, we will be able to prove that other are involutive as well. Excuse me. And then there are 3 relations between annihilators. The annihilator of the distribution E0 has to be contained in the annihilator of the Riemann tensor, has to be contained in the annihilator of the covariant derivative, and has to be contained in the annihilator of the second covariant. This for the annihilator of the second distribution. Okay, so these are necessary and sufficient conditions for local mechanical feedback linearizability.
Witold, sorry to interrupt.
Sure.
Can you explain in more detail what is the annihilator of the Riemann tensor?
Yeah.
Because, I mean, the Riemann tensor is not a distribution, right? So
Sure.
How exactly is defined?
I mean, it has only one upper index, right?
Right.
Okay, so I apply a differential one form to it, and the result is the sum of let me call it omega I R I J K L. So it's the tensor.
It's a sum of 3 forms.
Yeah.
Right.
So
okay. So you require that sum to be 0.
Yeah. So in other words,
okay.
yeah, I apply the form to that, and I want this 3 contravariant tensor to be 0.
Okay. Thank you.
Yep. And the same, the same for the second covariant derivative.
Okay, thank
an example. So it's a mass, M3, to which we attach a spring and a double pendulum. So once again, there are 3 degrees of freedom. That's the position of this mass, and 2 angles, x1, x2. Now there are 2 controls, because we can apply a torque to the first pendulum and a torque to the second pendulum. And then the question is it mechanical feedback linearizable? Yes, so all conditions are satisfied. The system is mechanical feedback linearizable. That means it is linearizable, although, I mean, written down in natural coordinates, it's nonlinear. You can get rid of all nonlinearities, and moreover, you can do it in such a way that you preserve the mechanical structure of the system. That means your diffeomorphism will be an extended point transformation, and your feedback will be quadratic with respect to velocities. For this system, the mass matrix, the kinetic energy, the metric tensor, if you prefer, is not Euclidean, but in well-chosen coordinates it is. And the drift is also linear vector field, and the control vector fields are constant up to feedback transformation. A comment about all those linearization procedures. So that's our mechanical drift. And actually, look, it consists of 2 vector fields. One is the geodesic spray, or semi-spray if you prefer. That's this one, which is coming from the geometry of the problem, geometry of the configuration manifold. And then this vector field, which is the external non-controlled action of the system, which is the vertical lift of a vector field E on Q. So there are those 2 vector fields, this one and that one. And actually, there are 2 possible ways to attack the problem. And what I presented is an illustration of those 2 ways. Either you linearize the virtual system, that means this part, and then you want to make sure that in suitable coordinates, the geodesic spray is linear. Christoffel symbols vanish. Only this part remains. Now, I'm saying in suitable coordinates, because if you linearize this, linearizing coordinates are not unique. So among them, you can look for coordinates that will kill Christoffel symbols. Or you can do the other way around. You can start to get rid of Christoffel symbols, and this you can do if and only if the Riemann tensor is 0. And then you have to be sure that in Euclidean coordinates, this system is linear, I mean, the drift and the G vector field. Now, here the freedom is much smaller, right? Because, I mean, once you get rid of Christoffel symbols, then only linear transformations preserve the fact that Christoffel symbols are not there. And that's the second approach that I discussed with you. Now, another comment is that for state space linearization, we gave you local result and global result. For feedback, only local results. Why is it so? For the following reason, that as you remember, the crucial condition that we had to add to local ones was completeness of some vector fields. Now, if you apply diffeomorphism, completeness is preserved, of course, but if you use feedback transformations, completeness is not preserved, because feedback transformations allow to add to the drift something, and if you add two complete vector fields, the result need not be complete. And the same with multiplying the control vector fields by functions. Even if control vector fields are complete, multiplying them by smooth functions may change completeness. So that's the reason for which going from local to global In feedback linearization, it's much more difficult. Okay. So that's the example I discussed with you. Yeah, I will skip feedback in input-output linearization, and I will come back to conclusions. So I discussed with you mechanical control systems. So I propose you a definition of mechanical control systems. Observe that there were no terms linear with respect to velocity. So all my systems were sort of conservative. Although my vector field E was not potential, but still there was no an explicit dissipation, like no damping. So this is a natural question for future research. Mechanical linearization of systems with dissipation for system for which but the right-hand side contains not only terms that are quadratic with respect to velocities, but also linear with respect to velocities, but with coefficients that depend on configurations.
So if I understand correctly, nothing is known about this? This has never been attempted? The dissipative case?
Let me put it like that. Nothing is published about that. We know something about that, but we are still not, I would say, extremely happy with the result that we are having. That we are working on it.
Okay, thank you.
But nothing is
published yet.
Published.
Thank you.
I propose two kinds of mechanical linearization: state space linearization, meaning just acting with a diffeomorphism locally, that means changing coordinates. In other words, systems that are MS linearizables are systems whose nonlinear nature is not intrinsic. They are nonlinear because we have chosen wrong coordinates. I mean, physically perhaps more natural, but systems in which evolution is nonlinear because of a bad representation. A better representation, the evolution is linear. And another linearization, which is feedback linearization, which is more general, more popular, and which allow for more systems to be linearized. For both classes, we presented necessary and sufficient conditions for mechanical state space linearization and mechanical feedback linearization in both controllable case at the beginning, and then general case, non-controllable in particular, in the second case. Okay, and as I said, I mean, a natural question for future research is mechanicalization of systems with dissipations. And last but not least, for systems with non-holonomic constraints. I mean, my systems were with no non-holonomic constraints, no constraints. The problem is that systems under non-holonomic constraints are never linearizable in the sense that I discussed today. Neither state space nor feedback. They can become linearizable using what is called dynamic feedback. That means you have to add some extra dynamics to your system. So, I mean, there are terms that are linear with respect to velocities, and those terms you cannot get rid of by just applying a diffeomorphism. So you have to add new dynamics to the system. That's a very interesting problem, and some results are known, but it's mainly open. So it's another possible directions of future research. Thank you very much for your invitation. Thank you for your questions. And I will be happy to answer other questions if there are still any.
Great.
There are few minutes for questions, so whoever wants to say something, comment, or ask, please feel free.
I have a lot of questions, but I don't know if there's enough time to ask all of them. So one question which I think is sort of natural is what happens in the Hamiltonian case? How does this relate to the control theory of Hamiltonian systems, and how does your notion of mechanical linearizability of a control system translate to the Hamiltonian language when everything is conservative?
Okay, so I mean, on one hand, our systems are less general than Hamiltonian systems, because okay, you can rephrase what I said on the cotangent bundle, there is no problem.
You assumed your drift, your drift will have to be coming from a potential, I guess.
Exactly. Right? So that's what I wanted to say, that on one hand, it's what I'm doing is more general, because I accept non-potential forces. So I will have to limit myself to potential forces, of course. On the other hand, I mean, my approach is so in the sense I have just said, is more general, but on the other hand, it's more general. On the other hand, it's more restrictive, because I will have, you know, a Hamiltonian system on the cotangent bundle, not just a general Hamiltonian system. So not much is known about linearization of control Hamiltonian systems, although theory of Hamiltonian control systems is well known, as developed by Arjan van der Schaft, Peter Crouch, and many other people. So it's a natural question. I agree, and yeah, it would be interesting to see to what extent the two approaches differ.
I mean, that relates to this CAM theory and so on. So it could be interesting to see if you could apply some of those tools to this problem of mechanical linearization.
Yes, it does, but
I mean, by this Hamilton-Jacobi formulation.
Yes, I agree. But if you take the pure CAM theory, then you are just given one vector field. So this is in a sense like the last part of my talk, because if you don't assume controllability, then you may reduce your problem just to a single vector field. But in my case, even if my system is not controllable, I still have controls. That means some vector fields, maybe those vector fields G's, they do not generate the whole tangent space together with their brackets, but still they are there. In other words, my starting point is 1, the drift, plus m vector fields, while in the classical CAM theory is just one vector field. So of course, those extra vector fields, they provide extra structure and extra information. So in a sense, it's easier to deal with them. On the other hand, the theory is richer, because immediately you have more than just a vector field. You have all that you can do with an m plus one tuple of vector fields. So either, you know, Lie algebra of vector fields, or in the case of feedback distributions and affine distribution.
Okay. May I ask another question, Katarina?
Yes, please.
Yeah. So another question is about connection to foliations and non-commutative geometry. So in this formulation, in terms of a tower of distributions, right? You had this ascending sequence of distributions.
Yes.
So you needed a constant reg condition and complete integrability as the first two conditions. So this, I can view this, I can integrate it, these are by the Frobenius theorems, right? Because these distributions have to be integrable. I can translate this geometrically into an ascending tower of foliations.
Yes, you are perfectly right.
Right, but it's not clear to me what this mechanical conditions, because you wanted this mechanical linearizability. These last two conditions mean geometrical in terms of foliations. And I'm wondering if they can be translated in terms of some kind of geometric structure on these foliations, and what this means if I want to now apply Cohn's standard trick, right? Try to go to this non-commutative space of leaves. Does this have an interpretation in terms of non-commutative geometry that might be interesting? Or if you want in terms of elliptic operators as fit to these foliations? Have you thought about that? Yeah.
So my answer to this second of your questions, I don't know. What would it mean for the non-commutative case? What concerns the first case, yes. If you forget the mechanical structure, but you perfectly were able to catch the geometry of the problem. This is sort of a repeated Frobenius theorem, this nested sequence is a sequence of distributions of constant rank involutive. So actually you can prove, and that's a technical lemma on which the proof is based, you can simultaneously rectify them. So actually you have a nested sequence not only of distributions but of foliations as well. Now, the question you ask, what does it mean for mechanical feedback linearization? I try to understand, and it's clear that it's a play, a game between the sequence of distributions and the vertical distribution, which is given for mechanical systems. So there must be some extra structure, but we were not able to rephrase it in terms of foliations. And I am afraid that it can be very difficult. The problem is that if you take a linear system, if you take a system with no mechanical structure, just a linearizable system, then but you can define those integral leaves by, say, assume that there is one control. So you are just looking a function whose differential annihilates the one before the last distribution. So all is up to this function. While if you mechanically linearize the system, this freedom is lost. So actually, linearizing coordinates are given uniquely up to linear transformation. So that means there is much more than just a foliation. It's some linear functions are sort of rigid in the problem.
Yeah, there's some more structure on this.
There is much more structure, and that structure is that rigid that the freedom you are given is not the freedom which is in the case of foliation, like one arbitrary function of one variable. Here, the freedom is reduced to just linear transformation.
May I also ask a question?
Sure.
Definitely.
Forget control for a moment. Just a basic question. You have a system of first order differential equation, ordinary differential equation. Can you tell when this system is linear in some coordinates?
In many cases, yes. In general, no. Because if you just take a system of equations, and you ask a very natural question, which I ask myself many times, when is this linear? And if you don't make any assumption, you have first take into account that among those equations, they are algebraic equations, not differential. So actually your system will not evolve everywhere on your manifold, but on a submanifold. And then you have to have some condition that will guarantee that this restricted state space is a submanifold and not just a set. Because as you know, I mean, if this algebraic constraint is given just by one smooth function, as you know, for any compact set, there exists a smooth function whose set of zero is this compact set. So it can be...
No, but I don't want to have any additional assumption. Just I want to know whether a given system is linear.
So then forget about differential equations. Take an algebraic system, and then the question when an algebraic system is linear. I mean, if you don't add some extra rank assumptions, how can you transform algebraic nonlinear constraint into a linear constraint? You need some constant rank type assumptions. But I mean, that's one thing. The second thing is that in that part where you have controls, you will have, as I try to explain, more vector fields, so more information. If your system is just one differential equation, one vector field, then your problem is when can you linearize a vector field? And as you know, this is a very difficult problem that started with Poincare. Its solution is still, I mean, if and only if conditions are not known. You have to study resonances, but then you have to study, I mean, all problems related with when you can smoothly or analytically linearize a vector field.
No, but there
can
are
be linearized.
different. This touches different concept of linearization.
That's
Yeah, so
linearization. You
yeah,
want it. Yeah, that's
so
exactly.
there is a problem when vector field, which is singular at a point, is
Exactly.
equivalent to its linear part. But this is not my question.
I understood that this is your question. You have a differential equation,
Yeah.
and with no other assumptions, you want it to be linear. So part of it is a control system, and this was what I was trying to solve. Part of this problem of your system is just a single differential equation, a vector field, and we know what are the problems. And part of it can be non-differential, can be just algebraic, and that's another kind of problem.
No, okay, I understand that they are serious problems, but I wanted to know what is your opinion about this problem. You think that without additional assumption, any theorem describing this linearity isn't possible?
This is what, yeah, because if your theorem is take like I started with, take this differential equation. It's the most general form of it. When is it linear with no other assumptions? All problems you have just mentioned are involved.
No, of course, linear systems have certain properties
Yes.
which this system might have. For instance, they admit a linear composition of solutions.
Yes.
So, of course, this is a very rare property for an arbitrary system of differential equation.
I mean, yeah, let me put it like that. I mean, if here all possible phenomena are combined, then for part of it, the part corresponding to control system, a necessary condition will be sort of a constant rank assumption. But on that part, which is purely one differential equation, there is no constant rank assumption.
Now you understand, linear systems are Lie systems.
Yes,
which is, yeah. So, of course, this is a first necessary condition.
No, but now you are changing the problem. If you want to characterize such systems by properties of their solutions, this perhaps is possible. But
yeah, so I just want to know whether the system is linear or no. Of course, I can use solutions for that, yeah.
If you know solutions you can use, but I would like, without solving this, which is difficult or impossible to be
No,
solved.
but then the question is nonsense, yeah. So
no, because under some extra assumptions, you can say when you can transform this to a system of linear equations, and in that huge system of linear equations that you will end up with, there will be a part corresponding to a control system. There will be another part uncontrolled, so just a single vector field. There will be another static part. So I think to split into those parts, I think I am able to do. To deal with the control part, I am also able to do. The static part perhaps as well, but the differential part with single vector field reduces to linearization of a vector field. So modulo the known difficulties of the I mean, on the formal level, if you don't care whether you do it in C infinity or analytic category, just on the formal level, if there are no resonances, as you know, among eigenvalues, you can formally linearize. So under this,
no, but this is different question. To be equivalent to its linearization is a different question.
But if you are linear, you are equivalent to its linearization.
No, but not necessarily in the coordinates you use.
Of course, in some coordinates, I perfectly agree with you.
No, but you do the linearization, you take the linear part in the coordinates you have.
No, the S equivalence I was talking about 1 hour.
Okay, maybe this
is
is
changing coordinates.
okay.
All was about changing coordinates.
It's a diffeomorphism.
It's a diffeomorphism, it's changing coordinates. I don't want this to be linear in given coordinates. I want to change coordinates in such a way that my object becomes linear.
Okay, I propose that we slowly close our session today. Thank you very much, Witek, for very nice talk, which I suppose, as all control theory, can have applications, which is always nice. And I would like to advertise the next seminar. Our Transcarpathian seminar started as a kind of two-part activity that we wanted it to include some students into the game, which we should probably admit we failed. However, next week there will be a living, breathing student giving a seminar. So I would like you to be there for him and encourage him, because it isn't a usual thing that a student is willing to work and prepare a seminar. The seminar will be partially about contact geometry and partially about geometric integrators. So you are all cordially invited. And Witek, thank you very much once more.
Thank you.
Thank you.
Last question to Witek, may I?
Yes, sure.
A little bit nasty.
Yes.
Why all specialists of control theory ignore recent results in
So it seems that the comment was that nasty that it was not.
I see. I understand. It is from above.
I don't know where it's coming from, but I didn't hear your nasty comment, so please repeat it, Pavel.
Karin, could you switch off your microphone? Hey, Pavel, try now.
I wonder why specialists in control theory ignore recent development of geometrical mechanics, mainly due to Tulciev and his collaborators. I mean, you start with a mechanical system which is not complete, because it refers to second-order differential equation only. And the mechanical system is something more. And to describe it in presence of external forces, which are sources of control, it needs a little bit different approach, geometric approach. So you start with something which is from very beginning under suspicion.
It's under suspicion, or it's not as general as it could and should be?
Under suspicion, because you know, if you have a control system, you need description of a mechanical system in the presence of external forces.
And that's
this is not, for example, Hamiltonian approach. And this is Lagrangian, but full Lagrangian you need. Not only part which is called Euler-Lagrange equation.
I mean,
Lagrange formulation is something more. What Kasia said, that Euler-Lagrange equation is in fact two form on second velocities, one form on the second velocities, and you know it's from the very beginning it is not easy to find out what is lost, what is added, and so on. In that, I would suggest to go to the very beginning and start to analyze all this procedure you use in control theory. I know this works of many specialists in control, and all time I found the same problem. It's no relation. On the other hand, specialists in mechanics, they know nothing about control theory. So I think we should meet somewhere.
Yes, I will arrive in Warsaw on April 15th, so it will be my pleasure to meet and to talk. And I mean, if your claim is that there is something that is missing in our, say, models of our equations for mechanical systems, I am willing to listen to you. What should we add? But I mean,
so find date and hours.
Beg your pardon?
Find the day and hours.
Okay. We will find the date and we'll find hours. Good. The same concerning your comments, Janusz, about linearization. I mean, I will be happy to discuss, I mean, linearization. The whole my life I am linearizing. That's the only thing I know to do. So if you have another viewpoint, another idea how the linearization should be considered or how should be attacked, it will be my pleasure to discuss.
Okay, thank you. I have no idea, of course, about the general solution of this problem, but I think this is one of the fundamental problems in this area of linearization of differential equation.
I agree. It's a fundamental problem in mathematics, because if we don't know what to do, we linearize. Then it would be nice to know what we can linearize and what we cannot.
It's not only because one uses linearization, linear version, somehow to refine, to prove the theorem on existence and something like this. And this linear version is in a different spaces.
Yes, this is true. But what I mean by linearization is not an approximate, I mean, a linear approximation. I would like to distinguish the two. I mean, linear approximation is, yeah, you just take a rubber and you erase higher order terms. I do not erase anything. All nonlinearities, they are compensated either by the action of a diffeomorphism or by the action of a feedback transformation. So it's linearization in the sense equivalence to a linear form. And this linear form in most problems can be taken as the linear part of the nonlinear object. But it's not linearization in the sense of a linear approximation.
Yep, I understand.
And Colin, thanks for your questions. And if you have any other, it will be my pleasure to continue discussing your questions by mail. Or so you can send me a mail with other questions you may have.
Thank you.
Okay, so I suppose we are done for today. Thank you once more for your patience, because we have extended our time for 20 minutes, and see you next week.
Thanks you.